So back to some tube equipment. I know you guys were getting a little bored of the solid state videos that I've been doing lately, and I thought I would introduce you to a classic instrument, the Boonton Q Meter. Q, what is Q? Besides being an important character on Star Trek, Q is a dimensionless figure of merit. And when you hear terms like, wow, this is really a high Q circuit, it kind of makes people think of magical terms, not reality. There's no suffix like milliamps or ohms at the end. What does a number mean? And we can cover some of that in this video. But as you can see, I'm wearing my electric radio shirt today, because I did write an article on Q and the Q meter that should be an electric radio probably this year. I just wanted to give a plug to that magazine. I do some articles for electric radio. This thing has been in publication since the late 80s, and it's really the only periodical that really covers the boat anchor era, military surplus, tube theory, and all of the gadgets and things that we have. I mean, you just open it up to a random page and you're going to find things like this. Here's an article on the alignment of the E.F. Johnson pacemaker and audio circuits. And it's really a very interesting magazine. So with our discussion of Q, we're going to learn about the Boonton 160 Q meter, and I have a long story on how I got acquainted with this. It's very useful when you're winding air-wound coils, and especially when you're dealing with toroids and winding on them. And you can see the differences as you add spacing to the turns, as you use different wire diameters, as you add Q-dope. Try to stabilize the cores through baking and so on. All of the different forms that you're using and materials that you're using to wind the coils around. So this is Q, the magic of a dimensionless number. So where did I get exposed to the Boonton Q meter? Well, that's back in the college days. I was a co-op student in Rochester at RIT. And at that time, there were a lot of companies that were being formed because General Dynamics had left town in '71. And of course, companies like Harris RF Communications and many of the RF amplifier companies were coming up. And people were doing startups trying to handle some of the abandoned GD equipment. So the little company I worked for, Radionics, we actually refurbed and recertified military transceivers, transmitters, receivers, and power amps. And some of these you might be familiar with, like the R1051 receiver, the GR106 transceiver, the T827 exciter, SC901, and so on. These all use the GD carousel, which is a bunch of front-end sticks all full of inductors that rotated around and gave you each band sort of in an automated way. Lots of knobs, lots of turning, and lots of inductors, and that's what the Boonton Q meter was all about. We were actually remaking a lot of these inductors and curing them, putting Q-dope on them, and then putting them in the oven, rechecking them on the Q meter, back and forth. So that's where the Q meter exposure came from. It came from my college days. What is Q? Before we get into the measurement instrument itself, let's discuss Q. Q factor is a dimensionless parameter that describes how underdamped an oscillator or resonator is. That is, will the energy in the tuned circuit transfer from the inductor to the capacitor forever with no loss? We've all probably considered the viability of perpetual motion or perfect power storage, and this is essentially what we're talking about with a resonant circuit. Once we add power to a resonating system, does the oscillation decay quickly and require us to put more power into it?
or does it continue to oscillate over a long period of time as it damps out? So that could be the difference between a high Q and a low Q system. The basic definition of Q is the ratio of the energy stored in the oscillating system to the energy dissipated per cycle by damping processes, like resistance and so on. Like dB, or decibels, it's a pure ratio term. This is not the definition we're used to, however. It turns out that the equivalent definition for the radio-tuned circuit is the frequency to bandwidth ratio of the resonator itself. Here we see some of the typical delta frequency versus the center frequency, and we're looking for the 3 dB difference between these two, and Q equals F over delta F. Note that we're always talking about AC here. We're not talking about DC. This is AC as applied to a resonant circuit. One of the primary factors in damping a tuned circuit is resistance. So formulas for RLC series and parallel tuned circuits are also derived. So R to us normally represents a pure resistor or pure resistance. But remember, we have to include all of the damping factors in the type of R we're using here. When we use this RLC type formula rather than the bandwidth formula, we say we are getting a true Q. The true Q is never really measurable in the world, but if we were to capture all of those losses and put it into that R factor, we would get what's called the true Q. What we actually measure with our instrument, because we're loading it a little bit, is the apparent Q. The apparent Q is what's on the screen or what's on the meter. So keep that in mind, that the actual Q or the true Q of the coil or the tuned circuit is always higher than what we can actually measure. Then when we put it into a circuit, such as a bandpass filter or an output filter on an amplifier, we talk about the term loaded Q. So here's a quick example of trying to test a tuned circuit. Normally I just hook up a scope and a generator that's feeding the tuned circuit with a 47K resistor. So we've got our 40 meter coil. Here's the specs on the coil. And then we use our formula. We find out that we have a Q on this coil of 445. And this is the true Q, you know, the unloaded Q, theoretical. The feed resistor and the scope both load the circuit, so they have to be taken into consideration. So the first thing we do is we put them in parallel, and then we want to convert them to an equivalent series resistance that we can add to the 0.2. So by manipulating terms, we can figure out how to go from parallel to series and series to parallel. But anyway, we're going to add the 0.106 to the 0.2 that we had with our original true Q, and that equals 0.3. So then we just use the original formula again, and now we use the 0.3 against it, and we can see that our Q has degraded from 445. Not markedly, we can still work with this 290, but I just wanted to show you the effect of loading on your tuned circuit.
Okay, let's take a look at the Boonton 160 Q meter. And the Q meter has a generator system over here. This is the tuning dial, and it covers several bands from, all the way from 50 kilohertz up to 75 megahertz in this case. It's an added band in red here. So this is the Armstrong Tickler feedback oscillator. It's got a low Z link off it that's going into the thermocouple. Here's how you set your band. Now I'm working with coils that are kind of in the middle of the HF band. These are kinds of coils that you would use between 6 and maybe 20 megahertz, 30 megahertz, that kind of thing. So they're in the 1 to 5 microhenry range. Here's a red core, red-black core, and it's got about 18 turns on it. This is going to give you about, 1.8 or 2 microhenries of inductance. Here's a similar air-wound coil, this is mini ductor, in the same kind of range. So we could set our oscillator in the 4.5 to 12 megahertz range, 7 megahertz, that's the 40 meter band. Good place to start. Now the next thing we do is we set our thermocouple ammeter, and this is the drive that's going to be into the tune circuit. So you want to make sure that the unit is well warmed up, and as you can see you have 2.5, 2, 1.5 and so on up to 1. These are your multipliers. You multiply what you get on the Q scale times the drive to give you the resulting Q. So first let's hook up the toroid, and if you put your hand on this one it's going to peg the meter. So hook up the coil to the ground side first and then to the hot side. I'm going to zero the meter with this little control here. I'm going to make sure that my drive is someplace where I can, count on the multiplication. So I set it for 2. Okay? So whatever we get on this scale, we multiply times 2 to get the final Q value. So this side is the side that has the variable capacitor that goes with the coil to produce the resonant circuit. So we're going to wander around with the capacitance until we get a rise. Ah, there it is. Looks like we're putting about 280 picofarads. Looks like it's about 95. So 2 times 95 is giving us just under 200 for an apparent Q on this thing. So could you believe that it could be around 190? So let's turn our drive down again, and let's stick an air coil on there. It doesn't have the self-shielding characteristics of the toroid, so it might not be as good of a measurement. Look we have a little bit of reading already. That's a good sign. Let's go up to 2 again. This is not by design. This is just something out of the junk box. It turns out that this guy is very close to the toroid. Isn't that interesting? And it needed about 275 puff to resonate. Here's the fine tuning. And we got about 120. So 120 times 2, 240. Does it make sense that the air inductor has more Q than the toroid? It should make sense to you. So when you're doing comparative, I might try to wind the same coil using yellow-black cores, see if that gives me better Q than the red-black cores. That's the kind of thing you're doing to try to optimize things. And I found this Q meter at the Nearfest Ham Flea Market in New Hampshire. There were 2 of them lying on their side in a mud puddle underneath a table, and I think I offered $5 or $10 for it, and they happily gave it to me. I washed it down with a hose and let it dry out in the sun and have not touched it. So it's been sitting in the shack now for a few months, and it's time to take a look inside to see what we have. Of course, the question on something like this that came out of the junk pile is, will it actually operate? Are the tubes good? The internal thermocouple, is it still good? And will it come back? And will I actually be able to calibrate it and make some measurements? Now, for heaven's sakes, the last thing you want to do with any piece of equipment that you found in a mud puddle is plug it in and turn it on. But you guys know that already. So here we are. I've removed the screws, and I love their packaging. The whole front just comes off, and the back is separate with a little power supply that looks like it's, it's its own separate little module, which is very nice. I will be able to work on that power supply completely independently of the Boonton Q Meter, and that is the first thing I'll be doing, is restoring that power supply. Now it looks like there's an old-fashioned type 45 tube here. That's just a triode. They're using it for some magic. And they have a battery tube here. I'm surprised haven't found a mouse in here, but we've got a little cleanup to do. So the power supply and cabinet is very happy to have been vacuumed out by the Electrolux. Most people had 110 volt power, but here we are in the 21st century, and we definitely have above normal voltages. I don't know if you can see it or not, but on the side of the Boonton case it says SAVE, save. So even the instrument itself is calling out for help. So we do need to take care of this rust issue here. Notice how they have taken the paint and screened it so that it doesn't cover this section. That means they want to have RF contact between the two sections. So coming out of that hole right down here is a Type 45 globe tube, a Sylvania. It's got the date on it, 7/13/1933. It is possible. The earlier unit, the model 100 Q meter, dates back to that time frame. But I don't think this particular valve is the original tube. Hard to say. Of course, to a collector, this is a gold mine because the tube's worth more than the whole unit. Next we have the tube that comes out of this socket, and this is marked 535. It is an actual tube made for Boonton Radio Corporation, and it has some paint on it that says 777, and it is a 1659. Now I believe this tube is 1940s vintage because 1659 would have been World War II type of nomenclature for the military. I think this is more the date on this unit. It's probably the 1940s. That ancient Type 45, I think, was put in after. Notice the patent tags, placards that are put on top of the Type 45 tube. Now that means they had to pay some licensing fees to those companies. But more importantly, these are shields against people wanting to copy this instrument and possibly make a knockoff. They were not only going to infringe on Boonton Radio Corporation's design, but they were going to contend with the giants of the radio industry, and nobody wants to do that. So these effectively squelched any competition. So here's a 45 from my junk box, and it's the ST style. It looks like it's reading good. It's fading a little bit, but it is good. Okay, here's the one that was actually in the Boonton with the rain falling on it. Let's put that in there. Let that warm up a little bit. Okay, the triode section of the 2A6 is good. So we saw that the power supply is asking for a 5W4, which is a metal rectifier tube, but they actually put a 5Y3 in, and the 5Y3 is reading good. Okay, who's surprised that the Boonton Q meter sitting in the mud puddle holding the guy line for the tarp in the middle of the rain, has good tubes. Nobody should be surprised. Remember, tubes live in a vacuum world. They're isolated from a lot of the nastiness around them. So I've just removed the turret assembly cover, and note these 3 screws down below that are hex heads are nice because you can just loosen them and the thing comes right off on the slotted cover. So it looks great. I mean, there's no dust inside, clean as a whistle. I'll just hit this with some contact cleaner and we'll be in business. So the pinch wheels on this instrument could be covered with grease. In other words, the vernier knob won't work anymore. Something coarse like a paper towel. Put a little bit of contact cleaner on it, and then, just hold it with a, with your needle nose pliers, and just move it back and forth. And what we're trying to do is get the grease off the pinch assembly. And now the vernier is going to work. Of course, this is after lubricating the bearings and getting the contact cleaner on the contacts of the variable capacitors. So this is the on-off switch, and I hit that with some contact cleaner, and I had to move this small lever so that it would engage it properly. This had to be adjusted a little bit, and a little grease on there, and now that switch, the on-off switch, and the rheostat are working okay. So I really did not do anything with the power supply unit other than testing the 5Y3 rectifier, and some of you may ask, should I try to reform the capacitor on the power supply? Next question. I replaced the capacitor with a 40 microfarad 450 volt cap, and we're going to try to bring it up. Other than that, it's ready to go. So let's first turn it on. Notice I have it connected to the unit. You have to use the on-off switch that's on the unit. Of course, not much is going to happen until the 5Y3 actually lights. So I'm up at about 1/3, and the tube is starting to light, and we're starting to get voltage. Tubes are out of the set, by the way. I'm just trying a high voltage test here. And there we are at 100%. 350 volts, basically unloaded. Okay, this is the first power up with it all in the case. The tubes are installed and lit. Power is on. I don't have a proper jewel for the pilot light, but I've got a plastic one screwed in. It screwed right in there. This is an uncalibrated instrument. I haven't done anything to it. I'm just using it as described. We're measuring our same coil in the 17 meter band around 18 megahertz. Of course, we had to lower the capacitance in order to resonate it. It's over 75, and we have a multiplier of around 2. So I would estimate this to be a Q of about 150.
In practice, there are 3 major ways to test Q using instrumentation. The first way you're probably already familiar with, and that's using either a sweep generator or a signal generator along with an oscilloscope to plot the 3 dB points on the bandwidth and simply calculate Q as the center frequency divided by the bandwidth or the delta frequency. The second way is called the ring down method. This is where you put a fast rising pulse like a square wave into the circuit and you look for the damping factor, and there's a formula for calculating Q based on that. The third way is the resonance peak method. The resonance peak method is the method that's actually used in the Boonton Q Meter. So let's look at these one at a time. First, we have the signal generator with the scope. You guys are pretty familiar with this. You want to use a high value feed resistor between 47K and maybe 470K, feeding the tune circuit, and then you're using a high impedance oscilloscope probe and you're trying to get the bandwidth. The second method, of course, this is the ring down method. Notice with the square wave generator, they're using link coupling, loose coupling into the tuned circuit. So that's very clever how they're doing this. Then using a differential 10-to-1 probe into the oscilloscope. So that's a little more work, but probably very effective in the lab, and once you've got it set up, it's going to be a nice system. So in the Boonton Q Meter, we're using the third method, which is the peak response method. And we're simply putting a high impedance vacuum tube voltmeter, a really high impedance voltmeter, looking at this point right here. And as the Q improves, the amplitude improves. It's very clever. So here's the actual circuit to do that. And the way they did it was by using a high frequency oscillator with a low Z tap, so a low impedance tap, like a few ohms, driving a thermocouple ammeter. The thermocouple, of course, uses dissimilar metals, and the dissimilar metals always give a positive and negative response the same direction on the meter, depending on which side the metal is on. And in effect, we're measuring the current going into this very well calibrated resistor. And of course, through Ohm's law, we know that this represents the amount of power that we're putting into the tuned circuit. Now, the resistor is at a low enough value that it does not disturb the tuned circuit that much, so you get a pretty accurate reading. The next challenge, of course, is to design a high impedance RF voltmeter, and that's what the Type 45 tube is doing. So we're measuring across the capacitor to get the voltage, which represents the Q. And then as we change the drive, we multiply the drive times what we read on the voltmeter, and therefore we get a calibrated output, a direct Q reading that's very similar to the peak reading that we get with the filter response itself.
And what are these two terminals over here? Actually, these two are for adding external capacitors, for extending range, or even for measuring capacitors. What's this jack for? Is that for headphones? No, that jack is actually used to hook up a counter. At low frequencies, you can measure the frequency of the oscillator without taking it off frequency or loading it down too much, just by connecting a counter into this point. And if you put your turret at a halfway position between any of the ranges, as you can see the meter went down, it disconnects the oscillator from the thermocouple, and now you can inject from an external generator into this point, and you can use a high quality generator as low as 1 kilohertz, and that's going to allow you to measure transformers and large inductors at low frequencies. So the Q meter also will work all the way down to 1 kilohertz if you use an external generator to drive it. What else can we do? Oh, using a little bit of math from their operating manual, you can measure the dielectric constant of insulators. So by now we've learned a little bit about the Q meter. As we can see, we're reading something around 125 with this air wound coil. If we put our finger on there, we upset the Q. And we know that we have the multiplier around 2. We set that on 2, multiplied by the 120, and we get a Q of 240 for this coil. And we also know that because the coil is so close to the chassis, and we don't have very long leads on it, that we've got some proximity effects that are damping the coil. So the actual or true Q is much higher than this. But when we're just making changes to our coil, we'll be able to tell in a relative way that we're making improvements or degrading it. Hope you've enjoyed this video on the magic of Q and the Q meter.